Why is Mercury the most difficult planet to visit despite being close to Earth? Even though Mercury is the second closest planet to Earth, this is also the most challenging planet to visit. But why? Is it because it's too close to the Sun? Because of its high temperatures? Or will the composition of the planet have something to do with it? The answer will surprise you. The closest planet to Earth is Venus. Yes, you heard right, Venus. Although it is popularly said that the planet more like Earth is Mars, the closest is Venus because it is only 25 million miles from the Earth at its closest point. Does that mean that the second closest to Earth is Mars? No. The second closest planet to Earth is Mercury, since the shortest distance between Earth and Mercury is 48 million miles. The average distance between Earth and Mars is about 55 million miles. During perihelion, the distance between Earth and Mars is drastically reduced to just 36 million miles. Yet this only happens once every 26 months. So most of the time, Mars is farther from Earth than Mercury. When humanity began exploring the solar system's planets with spacecraft, the first planet to be visited was Venus in 1962. Followed by Mars in 1965 and Jupiter in 1973. We had to wait until 1974 for the Mariner space probe to visit the planet Mercury for the first time. Subsequently, in the following years, several space exploration probes were sent to study the farthest planets of the solar system in 1974, 1979, 1992, 1995, 2000, and recently in 2007. Several missions have been launched to explore Mars and the outer planets, and even study asteroids and faraway comets. But Mercury did not receive a single mission for 30 years. Was it because the Mariner 10 exploration probe gave us all the information we needed for Mercury, and there was nothing more to discover? No, the Mariner probe only managed to fly over Mercury 3 times, and during those 3 flybys, it only managed to map 40% of the planet's surface. Scientists were very interested in continuing to study this planet, since it was fascinating for scientific research, and the reason why they had not sent more exploration probes to study this planet is that it was the most challenging of all. But why is Mercury the most difficult planet to visit? The most challenging planet. The reasons why it is so difficult to visit Mercury can be divided into 2: temperature and speed. Let's start with temperature. It's no secret that Mercury is the closest planet to the Sun. Because of this, the temperature on its surface usually reaches 806 degrees Fahrenheit. These temperatures are very high for the circuits and components of any space exploration probe, so the ships sent to the planets closest to the Sun must be equipped with protective panels that protect the equipment from the scorching sun temperatures. These panels are usually placed on only one side of the ship, and with the help of the communication antennas, these are always kept pointing at the Sun to protect the ship's instruments. Secondly, we have the most crucial reason it is so difficult to send ships to Mercury: the proximity to the Sun. As you know, all bodies with mass exert a force of gravitational attraction that attracts other smaller objects towards them. The Sun is the most massive object in the entire solar system. This means that as the ships approach the Sun, you are accelerating more and more until there comes a point where they become difficult to control. This is one of the problems that have most caused the loss of space probes in the vicinity of the Sun. Maneuvering such an accelerated ship only with rockets is a challenging task to achieve, since usually space exploration probes do not carry as much fuel because they are much smaller than a human crewed ship. Minimize weight as much as possible. When it comes to spacecraft, engineers will always try to keep everything as light as possible, because the heavier a ship weighs, the more fuel it will take to get it off the ground. And the more fuel you need, the more expensive the mission will be, which is not at all attractive if you have a shoestring budget. The more fuel is placed in a space exploration probe, the less space there will be to place scientific instruments, which in the end are the most important. However, for 30 long years, scientists and engineers did not find any way in which a probe with little fuel could accelerate so fast as to reach Mercury. But that changed in 1985 when scientist Chen Wen-yen, an MIT graduate in nuclear physics, proposed a way to reach the planet Mercury with the technology available at the time. A risky route. To reach Mercury with the technology available at the time, Chen Wen-yen used his knowledge in orbital mechanics and developed a very particular route in which a spacecraft could travel an enormous distance, passing through several planets, which would slow it down enough to be captured by Mercury's gravity using very little fuel. Instead of sending a spacecraft directly to Mercury, Chen Wen-yen's new route charted a much longer path, in which the spacecraft would have to circle the Sun about 15 times before reaching Mercury's orbit. The probe in charge of carrying out this complicated mission would be the Messenger space probe, and to achieve this feat, the spacecraft would use the gravitational assistance of Earth, Venus, and Mercury, passing through the Earth once, Venus twice, and Mercury 3 times. With each flyby, the average speed of Messenger relative to the Sun would gradually increase, but the speed of the spacecraft relative to Mercury would decrease. How is this? Imagine you want to get on a train from a moving car. The train travels 60 miles per hour along the tracks parallel to Main Street and will pass through the general store precisely at 1 p.m. You're geared up for action, parked along Main Street in your car. At 12:59:30, you start accelerating down the street to intercept the train. Your car's starting point is closer to the general store than where the train is now, but the train is going faster, 60 miles per hour, and both are going in the same direction. As you accelerate up to 10 miles per hour relative to your starting point, you're going 50 miles per hour relative to the train. When you increase your speed relative to your starting point, the store, your speed relative to the train decreases. You're getting closer. You calculate your acceleration to pass the store at precisely 60 miles per hour while the train passes. You will go to 0 miles per hour about the train and 60 miles per hour about the store. Similarly, the Messenger exploration probe used the gravitational assistance of the planets to accelerate relative to the Sun, by getting closer and closer to the speed of Mercury. Once Messenger approached Mercury at the right speed, it could fire its main engine enough to be captured by the planet's gravity and begin orbiting it. Messenger Scan Probe. Messenger was a relatively small exploration probe launched on August 3, 2004, measuring just 1.3 meters wide and weighing just over a ton. The probe had a propellant thruster to help it maneuver and control its direction. This heat shield protected equipment from high temperatures and 2 solar panels that unexpectedly scientists used as solar sails that helped slow down the spacecraft's speed a bit due to the solar wind. The Sun emits solar radiation that spreads throughout the solar system. This radiation falls on the spacecraft and pushes them very slightly, though the thrust of the solar wind is tiny and typically does not influence the trajectories of the spacecraft. Because the journey of the Messenger probe was going to be so long and last so many years, it was a great help to slow down, and so the scientists tried to keep the solar panels pointing at the Sun at all times, so the probe saved a lot of fuel, which helped it extend its useful life. Messenger made all its orbits correctly and without many complications, passing through the Earth, Venus, and finally approaching Mercury 3 times until it managed to be captured by its gravity on March 11, 2011. Messenger's entire route covered approximately 4.9 billion miles and took approximately 7 years to complete the entire journey. Once Messenger reached Mercury's orbit, it began to perform eccentric orbits, alternating its distance between 125 miles and 9,320 miles of Mercury. This was done because Mercury's surface acts as a giant solar mirror that radiates a lot of heat into space. If a spacecraft stays too long close to Mercury, even with a heat shield, it could damage some equipment or, in the worst case, cause ship failures. The Sun has a brightness 7 times more intense on Mercury than on the Earth, which is why it was decided that the probe would perform eccentric orbits that would allow it to approach and move away from Mercury periodically to cool off from the high temperatures reflected by the planet. During the next 4 years, the Messenger probe would be responsible for sending thousands of photographs of the surface of Mercury, providing essential information that would help us understand the planet's chemical composition, the geography of its surface, and its internal structure. Finally, on April 30th, 2015, the fuel of the Messenger probe ran out, and the scientists in charge of the mission decided to crash the ship into Mercury, thus ending one of the most important missions in history. Thanks to the Messenger mission, a significant discovery was achieved. In the images sent by the probe, indications have been observed that could demonstrate the existence of frozen water at the poles of Mercury. Currently, the European Space Agency, ESA, and the Japanese Space Agency, JAXA, have launched a new mission that will be responsible for revealing once and for all if Mercury can have water or not. This is the Bepi-Colombo mission, and it is estimated that it will reach the orbit of Mercury in 2025. Why is it so difficult to get to Mars? In addition to Earth, Mars is the planet with the best conditions to host humans. Space agencies such as SpaceX or NASA are planning to take the next generation of astronauts to the Red Planet, but it has not yet been achieved. Why is it so difficult to get to Mars? Let's start. During the space race in the 60s, NASA successfully took 6 missions to the moon that placed 12 astronauts on the surface of our natural satellite. Having gone to the moon several times nearly 5 decades ago and is used to seeing astronauts travel to space almost routinely, having extended stays on the International Space Station, it's tempting to think that sending humans to Mars could be perfectly plausible today. However, to the current date in 2022, seeing the first humans on the Red Planet still seems to be distant. Science and technology tell us that sending human beings to Mars constitutes a challenge of enormous difficulty and complexity that is far from everything that has been done so far in the history of human exploration of space. But the reason almost all others are derived from is one: distance. Mars is far away. We see astronauts frequently travel to space, to the International Space Station, the ISS. Before that, for years, cosmonauts traveled to the Mir station aboard Soyuz ships, and currently taikonauts travel frequently to the Tiangong Space Station in China. Popularly, one has the impression that the place to which one travels in these missions is very distant. However, the typical altitudes at which these stations and spacecraft orbit Earth are a few hundred kilometers. The ISS, for example, orbits the Earth at an altitude that is equivalent to the distance in a straight line between Madrid and Almeria, about 400 kilometers. This space region to which humans routinely travel is within the so-called region of low Earth orbits, and technically we call it LEO, low Earth orbit. Lunar manned travel involves traveling beyond LEO orbit, since the moon orbits our planet at an average distance of about 380,000 kilometers, which is about 1,000 times farther than the altitudes of these low orbits. A crew and their spacecraft are put into orbit around the Earth shortly after launch, while the distance to the moon was covered on the Apollo missions in about 3 days. In the case of Mars, the situation is very different. Going to Mars involves moving from a geocentric mission to a sun-centered orbit, or heliocentric, which is a massive leap in the distances involved. Although the maximum and minimum distances between Earth and Mars vary within a specific range, the minimum possible distance is about 55 million kilometers. This distance is achieved every 26 months when Mars and Earth have an approach gap that lasts a few weeks. These are huge distances compared to all manned missions to space so far. The maximum distance to Mars is 1,000 times greater than that between the Earth and the Moon, and approximately 1 million times greater than the distance separating the Earth's surface from the LEO orbits to which one travels typically. In other words, a single trip to Mars is equivalent to 1 million trips to the ISS space station. Without needing to know anything else, the data about the distance to Mars already constitute an excellent clue to glimpse the magnitude of the problem. To appreciate it better, and without going into details related to propulsion methods or orbital dynamics, we will compare 2 human-crewed missions in round numbers: an orbital mission around the Earth for a single crew member and a lunar mission for 3 crew members. We start with the first orbital mission of the Mercury program of the early 60s, John Glenn's Mercury 6. In this mission, a 120-ton Atlas rocket was used, with a height of 29 meters. It managed to put a useful mass of 1.2 tons into orbit at an average altitude of 200 kilometers around the Earth. The cargo was a Mercury capsule with its only crew member, who remained in space for 5 hours. Let's see what changes the situation by having the Moon as a destination about 1,000 times farther away. In the case of Apollo 17, the last lunar exploration mission, its command and service module plus its lunar module, adding everything, are about 50 tons, were launched to the Moon by the mighty Saturn V rocket of about 3,000 tons and 110 meters high for a mission of a total duration of about 12.5 days, in which 2 of its crew remained on the lunar surface just over 3 days. In contrast, the third remained inside the ship throughout the mission. We see that the quantitative leap needed when we want to go to another world, that is 1,000 times beyond the low orbits of Earth, is enormous. On the one hand, the useful load to be launched happens to be 1.2 to 50 tons, while the size of the launch rocket happens to be 120 to 3,000 tons. Compare all this to a mission to Mars. For a mission to Mars, the crew will consist of 6 astronauts, and its duration, taking as an example the approaching gap in 2037, would be 174 days for the outbound and 201 days for the return, with a stay of 539 days on Mars. Such an extended stay on Mars would be necessary for the hope that the relative position between this planet and Earth would be optimal for the return with minimal fuel expenditure, which saves the shipment of hundreds of tons of fuel. This represents 914 days of stay on the red planet, or approximately 2.5 years. As we can see, the jump between the Moon and Mars is enormous, since doubling the crew and extending the duration to about 73 times that of the longest lunar mission means the need to provide and transport about 150 times more supplies. On the other hand, a longer duration of interplanetary travel means the need to provide the crew with more excellent protection against radiation, which is achieved in part by adding even more mass to the ships. Currently, this problem is not entirely solved. Another problem with a long-lasting trip is that things break down. Either the durability of the equipment will have to be substantially improved, or they will have to be able to be replaced by spare parts that will also have to be transported, which implies a greater mass. Cargo spacecraft visiting the ISS can stock up on spare parts when something goes wrong on board, but this option will not be possible on a mission to Mars. Anything that can break will have to be repaired or exchanged for the same parts on board. Tons of fuel for a single trip. Experience tells us that braking a train is much more complex than braking a truck, because the former has more mass and therefore needs more time to brake. Sending more mass to Mars also means transporting more fuel to accelerate all that cargo to Mars, but it also means carrying more fuel to stop when the ship reaches the planet. In addition to all the fuel necessary to return to Earth, we are talking about hundreds of tons of fuel that we will have to carry to Mars in some form. One option that some scientists propose is to use the minerals and gases trapped in the subsoil of Mars to produce fuel, but so far no system has been tested that can do this. So until we prove that something like this is possible, the only option will remain to use our fuel. And for the distances we've talked about, as well as for the round trip, in total the Mars mission will require carrying between 850 and 1,250 tons of fuel. This is a massive amount if we consider that the ISS has a mass of about 420 tons, and that a ship with which we are familiar, the Space Shuttle, could only send into space between 15 and 25 tons approximately, depending on the altitude of the final orbit. The Ariane 5 can put about 20 tons in low orbit around the Earth, like the Russian Proton rocket, with the most powerful ships of the time. Taking all that fuel into space would take us about 10 trips at least. Thus, we can already intuitively anticipate that a single rocket will not be able to be used to go to Mars, but that several rocket launches will be required, as powerful or more powerful than the Saturn V of the 60s, to assemble in space different propulsion elements, fuel modules, habitats, and ships, which will have to be sent to Mars separately and in advance, in addition to the spacecraft with the crew, which would be sent last. Although it depends on various factors, they will require in fact 10 rocket launches with the capacity of the Saturn V or similar. But remember, the total number of Saturn V rockets sent to the Moon in the entire Apollo program
was 9. The Saturn V was retired from service after the Apollo program, but holds the record even today as the most powerful operational rocket ever, capable of putting just over 120 tons into low orbit around the Earth and sending 50 tons to the Moon. It had to be specifically designed and built in its day to reach the Moon. The only rocket capable of dethroning the Saturn V could be the SLS rocket Space Launch System, which will have a similar or perhaps somewhat superior performance than the Saturn V. The effects of weightlessness. A time of 539 days out in weightlessness profoundly affects human physiology, especially worrying when arriving on a planet where no one can assist you. The ships that can be seen in the movies, with spacious and comfortable cylinder-shaped cabins rotating to simulate the acceleration of gravity, do not exist today. So astronauts who will go to Mars will suffer from weightlessness throughout the mission. It is not yet known precisely how they will recover when they reach Mars. For psychological reasons, 2.5 years is a very long time. Earth will be seen by the crew as a star-like point of light for most of the voyage, and barely noticeable on Martian night. The crew will have to live in a condition of permanent confinement in a small space in a situation of great stress, and with the impossibility of maintaining fluid conversations with loved ones on Earth due to the signal's travel time. Remember that radio signals travel at the speed of light, which is the speed limit in the universe. Still, even at that speed, communications have a delay of 8 minutes between message and message due to the enormous distances the signals must travel. Conversing with a loved one in real time from Mars will be practically impossible. To these problems must be added all the technological, and operational difficulties involved in taking a human-crewed ship to such a remote place. No human being has ever experienced such a large journey. The astronauts will spend months in weightlessness, subjected to radiation from interplanetary space. Once on Mars, they will face other challenges that are very difficult to overcome, such as the fact that they will be locked 24 hours a day in a cabin probably equal or even smaller than the ship they used to get there. Although some enthusiastic and optimistic people about interplanetary travel say that humanity already has the technology and everything it takes to go to Mars, science tells us that we are not ready yet. The difficulties and challenges that arise from interplanetary travel are still considerable and difficult to overcome, but we may have the technology to achieve it. We only need the budget and time to plan things well. NASA has estimated that with modern science and technologies, it will be possible to take the first humans to Mars before the end of this century. Others think that in reality, there is much more to be done than that, and the most optimistic think that it will be achieved in the coming years. What do you think? Do you think we will be able to get humans to the moon very soon, or do we have many problems to solve? Let us know what you think in the comments of this video. Is it challenging to get to Jupiter? Why have we never seen its interior? Jupiter is the most visited gaseous planet of all. Throughout the history of space exploration, it has been visited by 9 spacecraft. However, so far only one ship has managed to cross its dense atmosphere to observe its interior. Is it tough to land a spaceship on Jupiter? What's inside the gas giant? The problem with speed. Jupiter is the 5th closest planet to the Sun, but it is not so complicated to get there despite being very far away. Because of the fact that it is the planet with the highest mass, its gravitational attraction force is vast, and thanks to that, spaceships do not work hard once they enter its gravitational field. But this is also a problem. Getting to Jupiter is relatively easy, but putting something into orbit around the giant planet is a more significant challenge. In 1979, the Voyager space probe took 1,546 days to reach Jupiter, but to get so far, the spacecraft had to acquire a very high speed. A trip traveling so fast cannot remain in orbit around any planet since it will follow its course. To place a spacecraft in orbit around any celestial body, it must adjust its speed. It must not go too fast to escape the gravitational pull, or too slow to be trapped by gravity and plunge into free fall towards the surface of the planet. The Voyager probe was too fast to be captured by Jupiter's gravity. To get into orbit, it would have to make use of rockets to help it slow down slowly, but at that time, the Voyager probes did not have such rockets equipped. Future missions that reached Jupiter did count on these rockets to slow down and enter orbit around the gas giant. Requirements to reach Jupiter successfully. In general, flights to other planets in our solar system are accompanied by high energy expenditures. For a spacecraft to reach Jupiter's orbit from Earth, it requires about the same amount of energy that it would require to lift it off from Earth's surface and place it in low Earth orbit. However, gravitational assistance can sometimes be used to help space probes, requiring less energy at launch, although this procedure significantly increases the time of the mission, which eventually means that the spacecraft must be equipped with some resource that allows it to replenish energy during the long journey, either with solar panels or thermal nuclear energy sources. An even bigger problem is that Jupiter has no solid surface on which to land. Because of its gaseous composition, there is a smooth transition from its atmosphere and its inner fluid. But the atmosphere is so large and heavy that any space probe descending through Jupiter's atmosphere would eventually be destroyed by the immense pressure and reduced to dust. Another problem is the amount of radiation a probe is exposed to reaching the planet, given the harsh particle charges around Jupiter. For example, the Galileo probe has orbited it for several years and has had markedly exceeded the amount of radiation for which it was designed. As a result, the scanning probe has suffered various technical problems and failures attributed to unrepaired radiation effects. Our visits to Jupiter: Pioneer 10 and 11, 1973 and 1974. Pioneer 10 was the first space probe to explore Jupiter, which did so in December of 1973, followed by Pioneer 11 13 months later. The Pioneer 10 probe was the first spacecraft in history to take the first images of Jupiter from up close, thanks to which we could observe that Jupiter was covered with storm clouds that could not be seen clearly from Earth. Pioneer 10 also took images of the Galilean satellites Europa, Io, Callisto, and Ganymede. It observed its atmosphere and radiation belts, which extended several thousand kilometers from the planet. Thanks to this mission, Jupiter's magnetic field was detected, which extends so far that all the solar system planets could fit inside it. Another discovery that we owe to the Pioneer probes is that, thanks to temperature lenses, it was possible to corroborate that Jupiter is mainly liquid. That is to say that instead of being called a gaseous planet, it should be called a liquid planet, since its main composition is metallic liquid hydrogen. Pioneer 11 was the first probe to take sharp images of the Great Red Spot. It made the first observations of its polar regions and obtained the first close images of the satellite Callisto, which is wholly covered with active volcanoes. Voyager 1 and 2, 1977 and 1979. The famous Voyager exploration probes traveling to the solar system's far reaches also used Jupiter's gravity to gain speed. Voyager 1 began photographing Jupiter in January of 1979 and made its closest approach on March 5th, 349,000 kilometers from the planet's center. Because of its higher resolution and shorter distance, most observations of moons, rings, magnetic fields, radiation, and the environment were made during the 2 days the probe was closest to the planet. The Voyager missions improved the understanding of the Galilean satellites. They contributed to the discovery of the rings of Jupiter that, until then, no one had seen because they are too thin to be detected with a telescope from Earth. Before the Voyager missions, Saturn was believed to be the only planet with asteroid rings. The probes took the first images of its atmosphere and revealed that the Great Red Spot is an anticyclone moving counterclockwise, in addition to other smaller storms near the main one. These missions discovered the Adrastea and Metis satellites orbiting close to Jupiter's rings, being the first moons of that planet to be discovered by a spacecraft. The third was Thebe. Together, the two Voyagers recorded great volcanic activity on the Io satellite, a total of 9 volcanic eruptions with evidence of others occurring between the encounter with the two probes. An unexpected discovery concerning Jupiter and becoming the first observation of active volcanoes in another planet besides Earth. In Europa, hundreds of lines were discovered and initially considered acts attributed to tectonic movements. However, thanks to the photography of Voyager 2, it was determined that the true origin of these cracks was because Europa is a moon with geological activity, and that it has at least 30 kilometers of crust in the form of a thick layer of ice. It is currently thought that beneath all of Europa's ice there could be an ocean of liquid water. Ulysses, 1992. The Ulysses spacecraft was designed as a 5-year mission to study the Sun's never-before-examined North and South poles. Ulysses became one of the most prolific contributors to knowledge of the solar wind, interstellar dust, and the three-dimensional character of solar radiation, far exceeding the lifespan of its planned mission by 13 years, and collecting treasure troves of data on the solar wind, interstellar dust, and the solar activity cycle. The spacecraft also performed several technical feats, including an unprecedented gravitational assist maneuver on Jupiter to launch out of the elliptical plane and enter its solar polar orbit. After the probe's launch, Ulysses headed to Jupiter. It arrived in February of 1992 for the gravity assist maneuver that placed the spacecraft into its unique solar orbit that no other spacecraft had done before. Thanks to this, the probe managed to leave the plane of the ecliptic, where all the planets rotate and pass over the south pole of the Sun in 1994, and the North Pole in 1995. Beginning its second orbit of the Sun, Ulysses revisited the South Pole in 2000 and the North a year later. At the time, the Sun was near the peak of its 11-year activity cycle. Ulysses then returned to Jupiter's orbit on the long stretch of its 6-year circuit around the Sun. The mission ended on June 30, 2009, after disconnecting the probe remotely, unable to carry out further significant scientific activities due to the depletion of its nuclear power source. Galileo, 1995. So far, Galileo has been the only space mission to venture deep into Jupiter. During the mission, a large amount of information was gathered about the planet and its system. However, it was not as large as expected due to a failure in deploying the probe's transmitting antenna. Significant events during the 8 years the mission covered included multiple flybys of all Galilean moons, including Amalthea, the first probe to do so. In part, it witnessed the impact of Comet Shoemaker-Levy 9 as it approached Jupiter in 1994 and sent back atmospheric proof of the planet in December of 1995. An atmospheric probe was deployed from Galileo in 1995, which entered the planet's atmosphere on December 7th of that year. After descending with an immense G-force, it was destroyed by atmospheric pressure and temperature after crossing 150 kilometers of the atmosphere and collecting data for 57.6 minutes. The probe was subjected to 22 times the Earth's temperature at 153 degrees Celsius. It is believed that the probe was melted down and probably evaporated by the high temperatures, turning it to dust. Later, the Galileo probe ran with the same fate, although more quickly, after being deliberately directed towards the planet at 50 kilometers per second to prevent any failure to cause the probe to fall on the satellite Europa, contaminating it with human space debris. Among the scientific results obtained by Galileo is the first observation of ammonia clouds in the atmosphere of a planet other than our own. The atmosphere creates clouds of ammonia ice from materials from the depths. It also confirmed the extensive volcanic activity that was suspected on Io, 100 times greater than the Earth, considering the heat and its frequency as an example of what the Earth was in the past. On this moon, it also observed the complex plasma interactions of the atmosphere, which gives rise to electric currents similar to Earth's thunderstorms, but thousands of times larger. It also provided evidence confirming the existence of a liquid ocean under Europa's surface ice. It made the first detection of a large magnetic field around a satellite, Ganymede, something completely unexpected since, until then, it had never been seen that a satellite could have such a large magnetic field. The Galileo probe also provided evidence of magnetic fields suggesting the presence of salty oceans beneath the surface of Europa, Ganymede, and Callisto, as well as a thin atmospheric layer on all three moons, called the exosphere, indicating that all three satellites have a high probability of harboring both liquid water and possible living things inside. Cassini-Huygens, 2000. In 2000, on its journey to Saturn, Cassini-Huygens approached the planet, providing some of the highest quality images of Jupiter to date. One of the main findings of the space mission was announced on March 6, 2003, about the atmospheric circulation of Jupiter. The dark belts alternate with the illuminated areas of the atmosphere. For a long time, scientists believed that the areas with their pale clouds were the regions from which air emerged into the outer atmosphere, similar to how it happens on Earth. However, analysis of Cassini-Huygens images show that individual storm cells arise in bright white clouds, too small to be seen from Earth. New Horizons, 2007. On its journey to Pluto, New Horizons approached Jupiter for gravitational assistance. While on Jupiter, it made detailed measurements of the inner moons, in particular Amalthea. It measured the volcanoes of Io and studied the Galilean satellites, as well as other moons such as Himalaya and Alara. The probe also studied the planet's little red spot, magnetosphere, and thin ring system, as well as taking infrared images that help better understand its atmosphere. Juno, 2011. The last mission to reach Jupiter was Juno. This probe was designed to study the planet's atmosphere, origin, structure, and evolution within the solar system, and thus better understand its formation. Its main functions are focused on creating a study and map of gravity in its magnetic fields, Jupiter's auroras, and its magnetosphere. It will also study clues about the planet's formation, its core, water in the atmosphere, its mass, and its winds, which can reach speeds of up to 618 kilometers per hour or 384 miles per hour. Currently, the Juno probe continues to orbit Jupiter on a safe trajectory that protects it from the intense radiation emitted by the gas giant, and is expected to continue operating for at least 6 more years. When Juno's mission ends, it will have the same fate as Galileo. It will intentionally crash into Jupiter so that it does not contaminate other satellites, such as Europa, which can harbor water. According to experts, future missions to Jupiter will not be to study the gas giant, but to study its moons. In fact, the European Space Agency already has a date for such a mission, and it is called JUICE, which means Jupiter Icy Moons Explorer, a mission that will take off in April of this year and that will aim to make a detailed observation of the gas giant planet and its 3 large oceanic moons, Ganymede, Callisto, and Europa, with a set of remote sensing instruments for organic matter. The mission will characterize these moons as planetary objects and possible habitats that could be humanity's following settlements. Why is it so difficult to get to Saturn? Since space exploration began, only 4 spaceships have managed to reach Saturn, but only one managed to enter the planet's bowels and reveal what is hidden under its cloud-filled atmosphere. Is it difficult to get to the planet with the giant asteroid rings? The gas giants. One of the main reasons Saturn is so difficult for our spacecraft or space exploration probes to visit is that it is part of the planets known as gas giants, which are very far from Earth and the Sun. Any spacecraft destined to visit the outermost planets of the solar system must meet specific requirements that are very difficult to achieve. One such requirement is that the spacecraft must have a nuclear battery that provides it with electrical power for all its data transmission functions. These ships must carry this type of battery instead of the classic solar panels, because these planets are too far from the Sun. Because of this, very little light arrives, and the solar panels fail to provide enough energy for the operation of the ship. Due to the lack of light, it is necessary to incorporate batteries that work with nuclear thermal energy. Still, the problem with these batteries is that they weigh a lot, which considerably increases the cost of the spaceship. In addition to the fact that the heavier it is, the more fuel is also needed to take it very far, compared to the energy needed by exploration probes that use solar panels. Gas giants like Saturn are located beyond the asteroid belt. In these regions, the temperatures are very, very low, which is why the ships that are sent to explore these planets must have isolation systems to the low temperatures of the interplanetary medium. And of course, one of the most important reasons why it is tough to reach Saturn is that it is 1.3 billion kilometers from Earth. To cover this distance, a large amount of energy and fuel is necessary at the time of launch, which is why the probes that have visited Saturn have been supported with the gravitational assistance of Jupiter. Too far for telescopes. Seen from Earth, Saturn appears as a yellowish object and one of the brightest in the night sky. Observed through a telescope, the two most giant rings, classified as A and B, are easily seen. The two most minor, classified as D and E, are only seen under optimal atmospheric conditions. Before the invention of the telescope, Saturn was just another planet in the sky. It was known to be the farthest of all, but there was no more information about it, nor about its asteroid belts. Galileo was the first to observe the rings in 1610, but the low inclination of the rings and the low resolution of his telescope made him think at first that they were large moons. Using better observation tools, Christian Huygens could clearly observe the rings in 1659. In 1859, James Clerk Maxwell showed mathematically that rings could not be a single solid object, but must be the grouping of millions of smaller particles. Today we know that the particles that make up Saturn's rings are composed mainly of fragments of rock and ice, and that they rotate at a speed of 48,000 kilometers per hour, 15 times faster than a bullet. Missions to Saturn. 4 American spacecraft greatly increased knowledge of the Saturn system: the Pioneer 11 probe, Voyagers 1 and 2, and the Cassini-Huygens space probe. These spacecraft carried cameras and instruments to analyze the intensities and polarizations of radiation in the electromagnetic spectrum's visible, ultraviolet, infrared, and radio regions. They were also equipped with instruments for the study of magnetic fields and the detection of charged particles and interplanetary dust grains. Pioneer 11. The first spacecraft in history to visit Saturn was Pioneer 11. This was one of the first probes of NASA's space exploration program. It was launched from Cape Canaveral on April 5, 1973. After successfully traversing the asteroid belt on April 19, 1974, its velocity was adjusted to place its trajectory close to Jupiter. During its flyby of Jupiter on December 4, 1974, it imaged the Great Red Spot, made the first observations of the polar regions, and determined the mass of the satellite Callisto. On September 1, 1979, it arrived at Saturn, taking the first close distant photographs of the planet, where it discovered 2 new satellites and other rings. After its encounter with Saturn, it continued its route outward from the solar system, studying the solar wind's energetic particles. Unsurprisingly, the Pioneer probes got their energy from a radioactive isotope source, RTG, instead of solar panels. These generators kept the ships on, so once they ran out, they stopped working in 1995. As was done with the Pioneer 10 probe and with the Voyager spaceships later, the Pioneer 11 probe included a plaque on its structure explaining the probe's origin to a possible extraterrestrial culture. The plaque includes a figure of a man and a woman, the transitions of the hydrogen atom, and the position of the Sun and the Earth in the galaxy, which was intended to send a message from the human race to a hypothetical extraterrestrial race that will find the ships in the future and manage to decipher the information contained in the disks. Voyager 1 and 2. Before space exploration, only Saturn's largest satellites, such as Titan, Enceladus, Tethys, Dione, Iapeto, or Mimas, were known. Still, the exploration probes, Voyager 1 and 2, managed to make important discoveries about these satellites that until then were unknown. Among these discoveries, it was possible to confirm the existence of large amounts of methane in the largest moon of Saturn, called Titan. They also managed to observe huge geysers shooting large amounts of ice and water on the satellite Enceladus. Both Enceladus and Titan are fascinating objects for planetary scientists, since the first belief in the possible existence of liquid water at a shallow depth of its surface, based on the emission of water vapor in geysers, and the second presents an atmosphere rich in methane and similar to that of the primitive Earth. Likewise, the first high-definition images of Saturn were also taken, which showed a yellowish color with black lines of storms that occurred in its atmosphere. Cassini-Huygens. This was Saturn's most prolific and longest-lasting mission on this planet. This spacecraft discovered 2 new satellites, Metone and Pallene, which are very small and have irregular shapes. After discovering these two satellites, Cassini flew by the moon Phoebe, taking several pictures of its surface and making several measurements that helped us know that this tiny moon of Saturn could have water below its surface. Titan exploration. The Cassini-Huygens space probe bore that name because, in addition to an orbiter, it also carried a terrestrial exploration spacecraft. This was the Huygens probe that would undock from Cassini to land on the surface of Titan, Saturn's largest moon. On January 14, 2005, the Huygens probe successfully descended on Titan's surface in a region known as Adiri, obtaining images during its descent and on the surface. The panorama during the descent shows gentle hills with drainage channels. The channels seem to lead to a close, wide, flat, and dark region where you can see an area of coastline and even islands and what appears to be a sea of methane, all in a foggy and arid environment. ESA scientists estimate that the probe could have descended over Titan's dark region. The image taken after landing shows a flat surface covered by stones in the form of rounded pebbles. The pebbles could be mostly made of water ice. It should not be forgotten that on Titan there is no liquid water on its surface, although there is frozen water. Such ice is present in the form of rocks. A week after landing, Martin Tomasco of the University of Arizona, responsible for the Huygens cameras, said, "We now have the key to knowing what shapes Titan's landscape. The geological evidence of precipitation, erosion, mechanical abrasion, and river activity that has shaped Titan is much like that which shaped the Earth in the past." Photos of Titan taken by the probe show a complex network of narrow drainage channels that descend from the Bright Mountains to flat, darker, lower regions. There are lakes, coasts, and islands strikingly similar to those on Earth, and it even rains, though not water like on Earth, but methane. But the similarities with Earth end here. Titan is a world ruled by its low temperatures of minus 179 degrees Celsius, with an atmosphere of nitrogen and methane. There, methane fulfills the role of water on Earth, forming clouds in its atmosphere. When it condenses, it forms a methane shower with particles that fills the torrents with a flowing black material. But now the canyons and lakes are dry because methane, like water on Earth, infiltrates under Titan soil, leaving traces of organic matter on the surface. Exploration of Enceladus. Following the encounters of the Voyager probes in the early 1980s, planetary scientists postulated that Enceladus might be geologically active, given its high albedo, indicating a relatively young surface, and its location in the center of the E-ring, perhaps through a mechanism of water vapor escape from inside. In 2005, data obtained through several instruments on board the Cassini probe confirmed this hypothesis. In addition, it also found possible reserves of liquid water at shallow depths that erupt as geysers on the surface of Enceladus, which was one of the most important discoveries, not only of the mission, but of the history of space exploration. Cassini's high-resolution images show icy jets and high ice spikes ejecting large particles at high speed from Enceladus' surface. Several models have been considered to explain this process. Data and models show that the jets escape from liquid water deposits shallow from the surface. The proof in favor of a subsurface ocean of liquid water between 30 and 40 kilometers below the surface is that this moon is growing. However, a suggested alternative to such an ocean may be large ice caverns filled with water. More recent models show that its geological activity is incompatible with the fact that it is controlled solely by tidal forces. It is better explained by assuming the existence of such a geological feature, which makes this small moon an ideal target for the search for extraterrestrial life. The end of Saturn's exploration. The Cassini-Huygens mission was the last to explore the planet Saturn. This mission ended in 2017 when the spacecraft began to run out of power, and scientists thought of many options to end it, from sending it to wander through space to crashing it into Saturn to avoid any biological contamination with other satellites that could have life. In the end, it was decided to impact the probe against Saturn, as happened with the Juno and Galileo probes once its mission in Jupiter was over. In this way, it took advantage of a gap that exists between the planet and the ring of asteroids that surrounds it, and after making 20 orbits, it rushed against Saturn, burning in its atmosphere and becoming dust. This option was also taken to take advantage of the systems of the ship that were still working. Thanks to this, they were able to obtain important data about the clouds of Saturn that today help us understand a little better how this gas giant works. Today, there are no more spacecraft exploring Saturn, but a new mission called Dragonfly is being planned, sending a robotic drone to explore Titan's surface in 2027.
Why is it so difficult to get to Uranus, the strangest planet? Uranus is the only planet tilted. Because of this, one of its poles is always pointing at the sun and the other in the opposite direction. This makes it one of the strangest planets and, at the same time, one of the most unexplored. Uranus is the seventh planet in the solar system, the third largest and the fourth most massive. It is a gaseous planet that has no surface where humans can walk. For years, space agencies, in space to NASA, have sent various exploration probes to investigate the solar system's planets. Still, it seems that every time new missions are proposed to the planets, Uranus passes completely from being perceived, in fact, is ignored more than its farthest twin Neptune. To date, only one exploration probe has visited this planet, and it was Voyager 2 that quickly passed close to it in 1986 solely to gain momentum. So why is there so little interest in exploring this planet? Is it so difficult to reach, or does it simply have nothing to offer us? The rarest of all. Despite its bad reputation and few exploration missions, Uranus is not a boring planet at all. On the contrary, it is one of the strangest and most exciting planets. With a volume 60 times that of Earth, this planet has a compressed mass of toxic gases. Uranus is similar in composition to Neptune because the two are different from the other gas giants, Jupiter and Saturn. Because of this, astronomers sometimes classify them into a different category than what they call the icy giants. Uranus's atmosphere, although similar to Jupiter and Saturn, which is composed mainly of hydrogen and helium, contains a higher proportion of ice and water, ammonia, and methane, along with traces of hydrocarbons. It has the coldest planetary atmosphere in the solar system, with a minimum temperature of 49 Kelvin, minus 224 degrees Celsius. It also has a very complex cloud structure, arranged by levels, where it is believed that the lowest clouds are composed of water and the highest of methane. In contrast, Uranus's interior is composed mainly of ice and rock. Because of this, Uranus does not have a solid surface. In fact, none of the gaseous planets have it. There are no definite limits, nothing to stop or sail on, just a mixture of gases and liquids that continuously mix until they reach the core. Why is it the only one totally inclined? Uranus's axis of rotation is sideways concerning the solar system's plane, with an axis tilt of 97.77 degrees. This produces changes in the seasons in a completely different way than the other major planets. The rotation of other planets can be visualized as spinning tops, inclined concerning the solar system plane, while Uranus rotates like a ball rolling inclined. When the solstices of Uranus approach, one pole continuously faces the sun, while the other is in the opposite direction. Only a narrow band around the equator experiences a rapid day and night cycle, but with the sun very low above the horizon as in Earth's polar regions. On the other side of Uranus's orbit, the pole's orientation in the sun's direction is reversed. Each pole receives about 42 years of uninterrupted sunlight, followed by 42 years of perpetual darkness. Can you imagine that? A planet where the night lasts 42 years. This situation, where the atmosphere doesn't warm for decades, can lead to some interesting atmospheric properties that don't occur on any other planet. As the equinoxes approach, the sun aligns with Uranus's equator, creating a period of day-night cycles similar to those seen on most other planets. The most recent equinox of Uranus was on December 7, 2007, and the next will be in the year 2049. A consequence of the orientation of the axis is that the polar regions receive more solar energy during the year than the equatorial regions. However, the temperature of Uranus is higher at its equator than at its poles. The mechanism that causes this circumstance is still unknown. The reason why the axis of the planet is so tilted and are not known. However, it is speculated that perhaps during its formation, the planet may have collided with a large protoplanet capable of producing this orientation. Another possibility is that the gravitational perturbations exerted by the other giant planets in the solar system have forced it to tilt this way. a long and challenging journey. As we have appreciated, Uranus is not a boring planet. On the contrary, it is a fascinating and unique planet. But there is an excellent reason why, in the entire history of space exploration, only one mission has visited Uranus. It is challenging. The planet is nearly 3 billion kilometers or 1.8 billion miles from the Sun, 20 times farther away than Earth. As a result, any spacecraft will take up to 15 years to get there, using rapprochement gaps between planets to take advantage of gravitational assists. Another limiting factor that all spacecraft that are sent to the far reaches of the solar system have is sunlight. As sunlight is feeble as we move away from the Sun, instead of solar panels, the mission must employ a nuclear power source, which is much more complicated to build and operate. In addition to being much heavier, and as we have already mentioned in past videos, the heavier a ship is, the more expensive it is, and what space agencies least want is to make their projects more expensive than they already are. Remember that one of the factors that most hinder the execution of space exploration projects is almost always money. Space agencies must justify very well the cost of a mission so that the government is willing to finance it. Another problem that adds up is communication. In a video we made earlier about the Voyager probes, we talked about how difficult it is to communicate with spacecraft that are too far from Earth. The only way to communicate with a ship that visits the icy giants would be to place a large satellite dish capable of emitting signals that manage to reach the Earth. As you can imagine, this would mean, again, increasing the weight and dimensions of the spacecraft. Not to mention the difficulty of receiving and sending data at those distances. The radio signals sent by a spacecraft take more than 20 minutes to reach Earth, and the communication between the receiver and the sender would consist of 40 minutes, which is a long time. Therefore, a ship heading to Uranus would have to have programmed a series of tasks that would have to be executed automatically and without human intervention, something that, although it sounds simple, it is not if we contemplate that a spaceship moves at more than 20 kilometers per second in interplanetary space. An error of 1 millimeter in any direction would be the end. Another significant and little talked about obstacle is keeping both engineering and operations mission teams together for as long as it takes to complete the mission. This can be up to a decade between launch and the spacecraft's arrival on the planet. Although it seems insignificant, this problem is why many missions have had to be cancelled. Even others have been delayed years because the team that began working on a mission was not the same that finished it. Information or codes of great importance are usually lost in the passage from one team technique to another. This was just what happened with the Voyager probes, which used VHS-type films to send images, and software made specifically for this task was responsible for encoding them here on Earth. The equipment that performed that job, the software, and the people that knew how to use them no longer exist. So today it is impossible to retake images with the Voyager cameras, even if they work. Another example of this problem can be seen in the recent Artemis 1 mission that aims to take the next generation of astronauts to the moon. Many people wondered why the spacecraft and equipment that were used in the 60s were not simply rebuilt. The reason is that all that information was lost. The people who knew the codes of the computers, the passwords, those who made the designs, the mathematical calculations, most of them died long ago. Others replaced the equipment. In the process, all that information was lost, and therefore it was no longer possible to rebuild the ships that took humans to the moon for the first time. As you can see, even before considering what instruments will be placed aboard a hypothetical ship that Uranus will visit, you must consider all this. NASA's new priority. It has become clear that Uranus and Neptune are the least known planets in the solar system. Because of this, NASA has been trying for years to outline the characteristics of a mission to study these bodies in 2030. In 2017, a NASA study concluded that it was necessary to study both worlds. The problem is that there is no money to launch two high-cost probes to the two planets, so it's time to prioritize. One option is to combine this mission with visiting one or more Kuiper Belt objects. Another is to explore one of the two planets. Until now, NASA considered both worlds equally fascinating from a scientific point of view, but in a recent report by OPAG, Outer Planets Assessment Group, the agency has radically changed its mind, and they think that they should give priority to Neptune. Why Neptune and not Uranus? Well, because of, or rather thanks to Triton, the largest moon of Neptune. The decision does not cease to be curious because until recently, Uranus seemed to have won the battle to be the next protagonist of a space mission. Uranus and Neptune are equally fascinating. Voyager 2 discovered Neptune and was more active than Uranus. Still, observations from the Hubble Space Telescope and ground-based instruments have shown that the last planet can be as active or more active than Neptune. On the other hand, Uranus's moon system is the worst known in the solar system, which compensated for Triton's presence around Neptune. However, the proximity of Uranus was the main factor in its favor, since it allows flight times sustainable lower than those necessary to reach Neptune. But OPAG does not support any compromise solution that includes flyby probes to the two planets. The only valid option for them is to send a flagship mission consisting of a 7-ton orbiter equipped with an atmospheric probe that studies one of the ice giants and its system of moons in detail. And since there is no money for two orbiters, you have to choose. Studying the moon system of Uranus or Neptune on the one hand, the moons of Uranus are the most unknown. In contrast, we know that Neptune has Triton, a moon in which there is likely water. Triton has tipped the balance in favor of Neptune because the community of researchers dedicated to the solar system's ocean worlds has identified it as one of its targets. Neptune's largest moon probably possesses an internal ocean, a mantle of liquid water comparable to Pluto's. After all, Triton is a Kuiper Belt body captured by Neptune. Ocean worlds include Europa, Ganymede, Callisto, Enceladus, Titan, etc. They are a priority for NASA because they are the bodies with the most significant potential for habitability in the solar system. So according to OPAG, NASA's next flagship mission after Europa Clipper should be an orbiter to Neptune. So sadly, and for now, there is no mission to Uranus, at least in the next 20 years. Some scientists are proposing to NASA to prioritize this planet, since the study of exoplanets has revealed that Uranus closely resembles most planets found so far in other solar systems, so that it could be the most common type of planet in the galaxy. However, at the moment, there is still no clear proposal. Is it challenging to get to Neptune, the farthest planet? Neptune is the farthest planet in the solar system. Since its discovery, only one spacecraft has reached this distant planet, making it the most unexplored planet of all. But why has it only been visited once? Is it because it's too far from Earth? Or is there something else preventing us from reaching Neptune? The first approach. The only spacecraft to reach Neptune was Voyager 2 in 1989. This was the first time the human race has placed a spaceship near this planet. Although 143 years has passed since its discovery, we knew very little about this planet. Neptune is the farthest of the four giant planets, is 30 times farther from the Sun than Earth, and takes 165 years to circle the Sun. Since its discovery, Neptune has not yet given a complete turn to the Sun. Its diameter is about 4 times larger than our planets, but it lacks a solid surface where we can walk, just like all other gaseous planets. With the help of observations with telescopes from Earth, it was discovered that this planet has 2 moons. One of them is Triton, one of the most exciting objects in the solar system, since according to its light spectra, it could contain large amounts of liquid water. Although the telescopes of the time were very powerful, Neptune is so far away from Earth that it is impossible to observe its asteroid ring. Because of this, the data collected in a few hours by Voyager 2 gave us more information about Neptune than about a century and a half of astronomical observations from Earth. To scientists' surprise, Voyager 2 revealed a large dark spot on Neptune similar to Jupiter's famous red spot. It is a gigantic hurricane with winds that exceeded 1,000 kilometers per hour, being the most violent in our solar system. On Earth, the sun supplies the energy the winds produce. In the case of Neptune, the temperature at the top of the cloud cover is minus 210 degrees Celsius, so solar energy is insufficient to give rise to the winds observed by Voyager 2. Astronomers think that the planet follows a process of contraction from which it formed billions of years ago. This process would be the one that provides enough energy to generate these powerful winds. However, the general structure of the winds on Neptune has yet to be understood by scientists to date.
Observations from Earth had provided evidence of rings around Neptune. However, this evidence was inconclusive, as more than rings appeared to be pieces of rings, like thin arcs of matter swirling around Neptune. Voyager 2 helped us make this more expensive once and for all, and during its approach to Neptune in 1989, it found 4 complete rings, 2 of them thin and the other 2 wide. The thin rings are located near the orbit of 2 satellites thought to be responsible for their stability and therefore called shepherd moons. The 2 most extensive rings are formed by highly opaque material that reflects approximately 1/10,000th of the light that falls on them. This is why it would have been impossible to detect them from Earth. If we had not sent the Voyager probe 45 years ago, today we would not know of these rings of asteroids around Neptune. The reason why Neptune's rings are so opaque is that they contain a large amount of dust, which can only be explained if, in the vicinity of Neptune, there is a greater abundance of meteorites than in the innermost areas of the solar system. For more than a century, only one moon of Neptune, called Triton, was known. In 1949, Gerard Kuiper discovered a second satellite named Nereid, which rotates far from the planet. As happened in the previous encounters of the Voyager spacecraft with other planets, Neptune had more hidden satellites that were not visible from Earth. Voyager 2 discovered 6 new moons, including Despoina and Galatea, the 2 shepherd moons mentioned above. It also found Proteus, the largest of the new moons discovered by Voyager, which has a surface completely covered with craters, the largest of which is almost half the size of Proteus. Despite these findings, Neptune's largest moon, Triton, the one known for more than a century, remains the most interesting. A difficult journey. Being the farthest planet in the solar system, it is logical that space agencies think twice before carrying out a mission to this planet. The Voyager 2 probe took more than a decade to reach the orbit of Neptune, and this was thanks to the fact that it had several gravitational assists with which it took the momentum and thus shortened the travel time. Without those gravitational assists, it would have likely taken at least 5 more years to reach Neptune. Can you imagine that? A 15-year mission to reach a planet brings challenges that are very difficult to overcome. Neptune is more than 4 billion kilometers from Earth. Even the sun's rays become scarce at this distance. Due to the absence of light, any spacecraft sent to this planet must necessarily use a nuclear power source, since the solar panels will not capture enough light. Mounting a nuclear battery on a spacecraft involves several engineering challenges. Still beyond those challenges, these batteries considerably increase the spacecraft's weight, eventually making it more expensive. In summary, the difficulties that would arise to reach Neptune are the same as those that arise to reach Uranus, which is much closer. Despite all the difficulties that may arise in reaching Neptune, this planet has exciting features that are attractive to astronomers. Thanks to this, there is currently a proposal by NASA to send a ship back to this planet. A unique climate. Neptune's meteorology is characterized by very dynamic storm systems, with winds reaching almost 600 meters per second or 2,200 kilometers per hour, and almost reaching supersonic flow speeds. Although its composition is very similar, Neptune has a much more violent atmosphere than Uranus. Voyager 2 observed weather phenomena on Neptune during its flyby in 1989, but observed no comparable phenomena on Uranus during its flyby in 1986. In 2007, Neptune's upper troposphere of the South Pole was found to be about 10 Kelvin warmer than the rest of the planet, which averages about 73 Kelvin or minus 200 degrees Celsius. The temperature difference is enough for methane, which freezes in the troposphere elsewhere, to escape into the stratosphere near the pole. This hotter region is due to the tilt of Neptune's axis, which has exposed the South Pole to the Sun during the last quarter of Neptune's year, equivalent to about 40 Earth years. As Neptune slowly moves towards the opposite side of the Sun, the South Pole will darken and the North Pole will brighten, causing the methane release to shift to the North Pole. Due to seasonal changes, Neptune's southern hemisphere cloud bands have been observed to increase in size. This trend was first seen in 1980 and is expected to last until 2020. The long orbital period makes the seasons on Neptune last 40 years. The jewel in the crown, Triton. In addition to the exotic weather, Neptune is something that Uranus does not have. and this is the main reason why NASA is planning a new mission to Neptune and not to Uranus, which is much closer than Neptune. We're talking about Triton. With a diameter of 2,707 kilometers, Triton is the largest satellite of Neptune and the seventh in the solar system, as well as being the only large moon that has a retrograde orbit. That is, an orbit whose direction is contrary to the rotation of the planet, something exceptional in a body of such size. Because of this retrograde orbit and its composition similar to that of Pluto, astronomers consider Triton to have been an object captured from the Kuiper Belt by the gravitational pull of Neptune. Triton is composed of a crust of nitrogen frozen on top of a mantle of ice, which is believed to cover a solid core of rock and metal. It also has an average density of 2,061 grams per centimeter cubed, and according to observations of its chemical spectrum, it is composed of approximately 15 to 35% water in solid state, i.e., ice. This natural satellite is one of the few in the solar system known to be geologically active. Due to this activity, its surface is relatively young and reveals a complex geological history, from mysterious and intricate cryovolcanoes and tectonic terrains. After Voyager 2 passed through in 1989, enigmatic images revealed what appeared to be liquid nitrogen geysers emanating from its icy surface. This discovery left the scientific community astonished, since it completely changed the classical concept of volcanism, because until then, it was assumed that icy bodies should not be geologically active. Triton was the first exception to that rule. This natural satellite showed us that there must not necessarily be a rock fluid for geological activity. Still, it can also be nitrogen or water. Ice volcanoes. The fact that Triton has so few craters indicates that its surface is constantly renewed due to some geological processes. Valleys and ridges are in a complex pattern all over the surface, probably resulting from freeze-heating cycles and volcanoes. The Voyager 2 probe observed icy volcanoes, plumes, vertically spewing liquid nitrogen, dust, or methane compounds coming from below the surface, in smoke reaching 8 kilometers high. Probably this volcanic activity is due to the ozone warming caused by the sun, and not like the heating of the volcanoes recorded on Io. Healy and Mahalanni are the observed Tritonian cryovolcanoes, both named after water spirits from African mythologies. Triton is one of the 7 bodies in the solar system that possesses volcanic activity along with Earth, Io, Venus, Europa, Enceladus, and Titan. We could continue talking for hours about this fantastic satellite, but we need another video. If you want a video about Triton, the largest Neptune moon, let us know with a comment. Thanks to this satellite with enormous possibilities of hosting liquid water and perhaps even living beings, the OPAG, Outer Planets Assessment Group, has named Neptune a priority for space research, even above Uranus. OPAG wants to start developing a mission to Neptune before 2024 to take advantage of the 2028 to 2030 launch window to send a mission to Neptune. The probes to the ice giants must use Jupiter's gravitational assistance to reduce the duration of the trip, but Jupiter and Neptune are in the correct position every 12 years or so. With Jupiter's gravitational assistance, the probe would reach Neptune in the year 2043 approximately. However, to date, there still needs to be a clear proposal of which will be the ship in charge of revealing the mysteries of this unexplored planet. Why is it so difficult to get to Pluto? This dwarf planet is more than 6 billion kilometers from Earth, and the only spacecraft that has managed to observe it directly was New Horizons on July 14, 2015. However, this ship did not enter orbit around Pluto. It observed it once and continued on its way to the far reaches of the solar system. But why spend so many resources just for a straightforward approach to Pluto? For many years, Pluto was considered the 9th planet in the solar system and the farthest of all. Located at the far reaches of the realm of the Sun, it seemed that it would take centuries for humanity to reach this small world. However, the first opportunity to visit Pluto came much earlier than most scientists imagined. It was the year 1964 when the scientist at the JPL laboratory of NASA called Gary Flandro realized that between 1976 and 1978, there would be a gap of approach between the gaseous planets. So if a space exploration probe was launched on those dates, It could visit most of the outer planets using a series of successive gravitational assists, taking advantage of the unusual planetary alignment that occurs almost every 2 centuries. Shortly after, NASA launched an ambitious project called Grand Tour, which would be starring 2 twin TOPS probes, although in principle they should be 4. One of the probes would be launched in 1976 or 1977 to explore Jupiter, Saturn, and Pluto, while the second would visit Jupiter, Uranus, and Neptune. According to NASA's plans, the encounter with Pluto would occur in 1985 or 1986. After analyzing the ambitious Grand Tour project, NASA concluded that its cost would be too high, so the Grand Tour project and the TOPS probes were canceled. Shortly after, NASA would launch a new, more modest and less expensive project, and from there would arise the famous Voyager exploration probes. Voyagers were initially scheduled to follow the same trajectories as the Grand Tour project, and NASA retained the option of sending Voyager 1 to Pluto after it visited Saturn. If the mission had been approved, Voyager 1 would have flown by the Pluto system in the spring of 1986. Instead, NASA preferred to send the probe closer to Titan, Saturn's largest moon, rather than Pluto. So once again, any visit to Pluto was canceled. Why were missions to Pluto canceled again and again? The reason is simple. Pluto is too far away. A challenge for the technology of the time. The Voyager probes did not have solar panels since they were intended to explore distant planets. In those regions, the solar radiation was very low, and a solar panel could not supply enough energy. Instead, the probes had nuclear batteries that produced electrical energy from the thermal radiation emitted by a radioactive compound. NASA concluded that due to natural wear and tear, this source of radioactive energy could eventually be exhausted long before reaching Pluto. So instead of losing the spacecraft, it was decided to take the opportunity to visit Titan. No one expected that after visiting Titan, Voyager's power source would still work. It was simply a stroke of luck. After these missions, NASA declared that Pluto was a lonely, small, and distant world, so the ships that visited in the future necessarily had to be complex and very expensive. Many scientists thought it was better to spend that money on studying the giant planets and their dozens of satellites, so the 9th planet would have to wait. During the 80s, no serious proposal to explore Pluto emerged, although there were undoubtedly exciting projects. The most curious of these was the Interstellar Precursor Mission, IPM, study of the Jet Propulsion Laboratory, JPL. The IPM mission aimed to send a massive probe to the heliopause, the solar system's edge where the solar wind gives way to the interstellar medium, in a relatively short time. The probe would have a mass of about 90 tons. Yes, you heard correctly, 90 tons. That is the heaviest exploration probe in history, and therefore should be assembled into Earth orbit by more than 5 space shuttle missions. This spacecraft would be equipped with a nuclear reactor and use an electric propulsion system, NEP, with ion engines. And what relationship did IPM have with Pluto? Well, this had to carry a probe to study the 9th planet that would separate when passing through its vicinity. The orbiter would be similar to the Galileo probe for studying Jupiter. It would use a propulsive stage, that is, a rocket to reduce its high speed and place itself in orbit around Pluto, which would hopefully take place during the first decade of the 21st century. As you may be imagining, this never saw the light, since once again the cost of such a project would be exorbitantly high. Sparked the spark of curiosity. In 1989, Voyager 2 had its encounter with Neptune. This event revived interest in a mission to Pluto, since this was the only planet left to explore. In addition, Triton, Neptune's largest moon, had turned out to be a complex world with an atmosphere, polar ice caps, and nitrogen geysers. Observations from Earth indicated that Triton and Pluto shared a common origin in the Kuiper Belt, and therefore must be very similar, especially since it was discovered in 1988 that Pluto was also shrouded in a tenuous atmosphere. In addition, in 1978, Pluto's first moon, Charon, was discovered, so a probe could now explore 2 worlds for the price of 1. A mission to Pluto once again climbed the scientific community's priorities. One of the first proposals was the Pluto 350 mission. The name referred to the weight of the spacecraft, which should not exceed 350 kilograms, including the radioisotope generator, RTG, to produce energy. Pluto 350 was born 2 months after Voyager 2's encounter with Neptune. It was to include only 4 instruments: a camera, an ultraviolet spectrometer for the study of the atmosphere, a radio experiment to observe the atmosphere mainly, and an instrument for plasma analysis. Among the architects of the mission was a planetary scientist named Alan Stern, who would be a key piece in the history of Pluto's exploration. Scientists feared that the dwarf planet's atmosphere would freeze as the planet moved away from the equinox that had occurred in 1987, so the launch should take place as soon as possible. Like the rest of the spacecraft proposals to Pluto, the Pluto 350 mission was to fly by Jupiter to perform a gravitational assistance maneuver and thus reduce the flight time by 2 or 3 years, depending on the launch window. To place the ship on a direct trajectory to the gas giant, the mission had to be launched by a large rocket, a Titan III or a Titan IV, which was the most potent American launcher at the time. However, this requirement increased the cost of the mission. Paradoxically, the Pluto 350 mission suffered rejection from NASA for being too simple. This is because many scientists and engineers claimed that launching a 350-kilogram probe into the outer solar system was a recklessness that had no chance of success, considering that previously the Voyagers had a mass at launch of about 800 kilograms. In other words, NASA preferred a more complex and expensive mission, but with a guarantee of success, than a simple mission but with the possibility of failure. Missions that never saw the light of day. In an area of meager budgets, NASA focused on simple flyby missions. In 1992, JPL's Robert Stale went further and announced the Pluto Fast Flyby (PFF) mission, a tiny mission compared to anything that had been done until then. If Pluto 350 were once a small probe, PFF would be tiny since its mass would be less than 150 kilograms. A few years before, few believed such a probe could be built, but with the constant cuts to NASA's budget, these new low-cost missions became almost the only option. Years later, NASA rejected the Pluto Fast Flyby mission proposal and replaced it with a new mission called Pluto Express. Since David Jewett and Jane Liu discovered the first body in the Kuiper Belt in 1992, it was becoming increasingly apparent that Pluto was not a planet like the rest, but a member of this new family of trans-Neptunian objects. For this reason, the mission would be baptized as Pluto Kuiper Express, PKE. At 175 kilograms, PKE would be slightly larger than Pluto Fast Flyby at 140 kilograms and carry 9 kilograms of scientific instruments, although its design was similar. Ultimately, both Pluto Fast Flyby and Pluto Kuiper Express were canceled due to budget cuts, but a mission to Pluto remained a scientific priority, as the launch window from 2001 to 2006 was inexorably approaching, and then there would be no other chance. So, in desperation, in 2000, NASA created a public contest to choose a mission to Pluto. This strategy had worked very well on low-cost missions called Discovery, but never before had such an expensive probe been attempted. Since the mission to Pluto required a more expensive mission than a Discovery-type mission, but cheaper than a flagship mission, NASA decided in 2002 to create the New Frontiers category for this type of probe. This is how, on February 5, 2001, the winning proposal was the New Horizons. At first, it would carry 4 scientific instruments. These would be Percy, which included the ALICE ultraviolet spectrometer, the MVIC color camera, the LISA infrared spectrometer, REX, a radio experiment, LORRI, a black and white telescopic camera, PAM, for the study of particles. To reduce the mass and cost of the probe, the corners of the triangular structure were trimmed and the diameter of the antenna had to be reduced from 3 to 2.1 meters. The final mass of the vehicle reached 478 kilograms. The total cost of the mission would be $646 million in 2014. The probe was launched from Cape Canaveral on January 19, 2006. New Horizons approached Jupiter between February and March of 2007 to take advantage of the planet's gravitational assistance, and thus acquire a speed difference of about 4,023 meters per second, or 14,482 kilometers per hour. In July of 2013, the probe sent back the first images in which Pluto and its largest satellite, Charon, can be distinguished as separate bodies. As New Horizons approached Pluto, the images sent back gained resolution. Until the day everyone expected on July 14, 2015, The New Horizons probe passed 12,500 kilometers from Pluto's surface at a relative speed of 49,600 kilometers per hour, taking the sharpest images it had ever seen of what was once the ninth planet in the solar system. In addition to photographing Pluto, the probe also sent tons of information that had served to discover all the mysteries of this celestial body. Thanks to this, today we know that Pluto is a vast ball covered with ice with recent geological activity and that it could contain water. After the Pluto flyby, the New Horizons probe continued its journey to the solar system's far reaches. To date, no other mission has managed to reach this distant world.
Why is it challenging to get to Proxima Centauri? Proxima Centauri is the closest star to the solar system. However, with modern technology, it would take thousands of years to reach that star. Will we ever have the technology to reach the closest star to the solar system? For years, this star has been observed with the most powerful telescopes in the world, and thanks to this, we have discovered that the star Proxima Centauri has at least one exoplanet that could have the conditions to host living beings. This makes reaching this star a matter of great importance for humanity, since this distant world could have living beings or be a human settlement in the future. But how difficult would it be with modern technology to get to this star? In short, a lot. It would be tricky. It would be the most challenging feat that the human race could perform in the distant future, and one of the most important if it were to be achieved. Suffice it to say that in the modern era, even with the technology we have not managed to send a spacecraft out of our solar system, nor have we taken humans beyond the moon. Not a human being has set foot on another planet other than Earth, so you can be entirely sure that there is still a long time before we manage to send the first spacecraft to Proxima Centauri. But how long precisely? Do we have any estimated dates for when we might reach this star? Let's see what the science says about it. So close and so far. The fastest human-created object we've ever launched in the solar system is Voyager 1. This venerable probe moves away from the Sun at a speed of 17.4 kilometers per second, equivalent to about 540 million kilometers per year. But Proxima Centauri is 4.24 light-years away. At this speed, it would take about 76,000 years for Voyager 1 to reach Proxima Centauri, assuming it traveled toward it, which it doesn't. To reach Alpha Centauri within an acceptable time, the speeds we have to reach must exceed 10,000 kilometers per second. At that speed, we would arrive in 130 years, which can be somewhat annoying, considering that most humans die before the age of 100. If we travel at 25,000 kilometers per second, the flight time is reduced to 50 years. Half a century is not wrong for an interstellar trip, so this should be the speed we aim to achieve. A challenge if we remember that Voyager 1 moves at less than 18 kilometers per second. Clearly, we have no choice but to use propulsion systems other than the usual ones. So we better forget about the conventional chemical propulsion used by ordinary rockets. Why? Because if we want to reach 1% of the speed of light, or 3,000 kilometers per second, using conventional chemical rockets, we would need 1,026 kilograms of fuel for each kilogram of mass of the ship. That is, the ship going to Proxima Centauri would have 100 times the mass of Earth. Something completely impossible. On the other hand, if we want to travel to Proxima Centauri in this century, we must make certain sacrifices. For example, forget about human-crewed spaceships. Conventional space probes are infinitely cheaper and more powerful. In addition, we can conceive of a mission limited to flying over the Alpha Centauri system without breaking and entering orbit around one of the two main stars, which would mean enormous energy savings. What propulsion systems can we use? Ion and nuclear thermal propulsion. Electric propulsion, ionic or plasma, is currently used in several spacecraft and allows a specific impulse to be achieved for hundreds of hours. Nuclear thermal propulsion follows a bit further back. These propulsion systems are not bad for traveling through the solar system, but it would take 40,000 years to reach Proxima Centauri. It would probably be better to rule out these options now. VASIMR, Variable Specific Impulse Magnetoplasma Rocket.
This engine was created by Ad Astra Rocket Company, led by former Costa Rican astronaut Franklin Chang Diaz. The project intends to create a plasma ion engine that will serve as a cheap and efficient alternative as a propulsion power source for spacecraft. He mainly focuses on exploring other parts of the solar system, such as a possible trip to Mars. With this technology, the journey would be 10 times faster than the current one and enable manned trips to the Red Planet, reducing the time from 18 months to approximately 39 days. Let's assume that, despite complaints from many critics, Vasimer is an economically viable project. In that case, a spacecraft with the Vasimer engine would only take 2,200 years to reach Proxima Centauri. It's certainly much less time than using ion propulsion, but it's still overcoming the 1,000-year barrier, and unfortunately humans don't live that long, so this option is ruled out. Pulsed nuclear propulsion. Popularized by the Orion project of the 60s, this system seems like something from science fiction. But the truth is that the associated technologies have already been tested. A pulsed nuclear spacecraft moves by detonating nuclear devices a short distance from the vehicle. A special plate absorbs the shock wave with shock absorbers, which transfers part of the energy to the spacecraft so that it accelerates constantly. Orion was a perfect vehicle for traveling through the solar system, but this system is not so attractive for interstellar journeys. To begin with, nearly 300,000 detonations of nuclear fusion bombs, and not nuclear fission bombs as in the original Orion project, proposal would have to be used, which is quite possibly beyond our technological possibilities. An interstellar Orion project with a human crewed spacecraft would have a mass of 400,000 tons and a plate 100 meters in diameter. And even with these monstrous dimensions, it would take about 150 years to reach Proxima Centauri. Not bad for a generational spaceship, but it doesn't seem to be best suited for an automatic reconnaissance mission. Even so, it is a system to consider if we join it to other forms of propulsion. Solar sails. In the language of interstellar flights, a solar sail is not a simple photonic sail like that of the Japanese Space Agency's Icarus space probe. A solar sail consists of a vast parachute-shaped structure that, like a photonic sail, would use the radiation pressure of sunlight, and not that of the solar wind as is sometimes mistakenly believed, to accelerate the spacecraft to escape velocities from the solar system. But to take advantage of this system, it is necessary to deploy the sail near the sun. Assuming that in the next few decades we will be able to build giant ultralight sails capable of withstanding more than 60 Celsius of acceleration and thousands of degrees Celsius, a solar sail could travel to Alpha Centauri in 1,000 or 2,000 years. It is still long, but you can combine the system with others to decrease flight time. For example, the Medusa proposal of the 90s linked pulsed nuclear propulsion with a solar sail. In addition, an interstellar spacecraft could use a solar sail to visit Proxima Centauri and then maneuver to travel to Alpha Centauri A or Alpha Centauri B. Solar sails are an exciting technology for interstellar travel, although these are still in a primitive stage of development. If in the future we manage to develop them and make the most of their benefits by combining them with other technologies, they could be the ones we use for the first trip to Proxima Centauri. Laser candles. Laser sails are a specific case of propulsion systems using energy beams. These consist of a giant photonic sail propelled not by sunlight, but by a set of powerful super laser beams in Earth orbit or some point of Lagrange. Suppose we had a set of space lasers, 25 gigawatts of power. In that case, we could send a 100-kilogram ship, of which 33 kilograms would be the payload and the rest the sail, to Alpha Centauri in only 40 years. A fairly reasonable time considering that the Voyager spacecraft have been traveling non-stop through the solar system for more than 45 years and have not yet managed to leave. The lasers should constantly work during the 4 decades that the mission would last, and the sail would be limited to flying over the system. Still, we are facing a form of propulsion within the technological possibilities of our civilization. Of course, 100 kilograms is tiny, but if we use a slightly more massive ship, the flight time will shoot up to 100 years if we do not increase the power of the lasers. So initially, this technology only serves us for uncrewed missions. Although we cannot send humans to other stars with this technology, at the moment, this is the most promising method in the short, medium, and long term. Starshot Project. As surprising as it may seem, although reaching Proxima Centauri seems an impossible mission to achieve for modern technology, there is currently a research and engineering project developed by the Breakthrough Initiatives program that aims to develop a fleet of micro spacecraft, known as Starship, powered by solar sails, capable of traveling to Alpha Centauri at 15% or 20% of the speed of light. That is 60,000 kilometers per second. So it would take between 20 and 30 years to reach its destination and another 4 years to communicate to Earth its arrival. The trip would also include a flyby of the planet Proxima Centauri b, which has characteristics very similar to that of Earth and is also in its star's habitable zone. The central concept that would allow this project to be launched is explained in the article Work Plan for Interstellar Flight, published in April of 2015 in the scientific journal British Interplanetary Society by Philip Lubin, a researcher at the University of California at Santa Barbara. The concept of Starshot consists of the launch of a mother ship with a load of thousands of nano spacecraft, a few centimeters in size and a few grams in weight, which, when they reach a high-altitude orbit, will be released into space. Then, high-powered lasers placed in Earth's orbit would focus a beam of light to propel the spacecraft's sails individually and accelerate their maximum speed in minutes, achieving an average of 100 kilometers per second squared and an energy of 1 TJ blown into each sail, each one 4 by 4 meters. Suppose the spacecraft finds a planet with characteristics similar to Earth in an orbit of the habitable zone of Proxima Centauri system, a case that occurred with the ground-based telescopes at the end of August of 2016. In that case, the project will try to bring the nano spacecraft closer to a distance of 1 astronomical unit, or 150 million kilometers or 93 million miles from the planet. At that distance, the spacecraft's cameras can obtain graphic data of a high enough quality to know these characteristics. Each spacecraft would have the possibility of transmitting data to Earth using a compact laser communication system. The swarm of thousands of units would compensate for the possible loss of spacecraft caused by collisions with interstellar dust during their long journey. Although this project is currently still in the development phase, it is estimated that with adequate funding, it would be possible to make it a reality in just 2 decades. That is, we would be able to see the execution of a mission and the arrival of the first spacecraft to Proxima Centauri in the same century. But even if we don't discover planets or moons like Pandora from the movie Avatar in the habitable zone of Proxima Centauri, a trip to the nearest star is a significant challenge for humanity. A challenge that would allow us to understand better the processes of planet formation in the Milky Way, and in the process, understand how our solar system was formed. As Carl Sagan said, by the time we can visit other stars, we will have changed. Only a mature and brilliant species can face the vast abyss of interstellar space and overcome it. If we want to survive in the immensity of the universe and not fall into oblivion, humanity must travel to the stars. It is in our hands to make this dream come true. Will we be able to meet the challenge?